I'm Dr. Sabnayan, Assistant Professor, Department of Electronics and Communication, Rajagiri School of Engineering and Technology, Kakinad, and I'll be dealing with second part of second module under Digital Signal Processing for S5 EC students. The topics that are covered are decimation-in-frequency FFT algorithm and inverse DFT computation using decimation-in-frequency FFT algorithm. In direct computation of endpoint DFT, the total number of complex additions are n into n minus 1 and total number of complex multiplications, that is n square. And FFT is a method for computing DFT with reduced number of calculations. The computational efficiency is achieved by using a divide and conquer approach. The present discussion focuses on decimation-in-frequency FFT algorithm. Okay, and we'll be dealing with radix 2 FFT algorithm, and in radix 2 the value of capital N should be equal to 2 raised to m. Okay, and in radix 2 FFT algorithm the total number of complex additions is reduced to n into log n to the base 2, and total number of complex multiplications that is reduced to n by 2 into log n to the base 2. Now let us see the derivation of decimation frequency radix 2 FFT algorithm. We begin with the original DFT equation, okay, and we split it into two summations. One involves sum over first n by 2 data points, and the second sum involves last n by 2 data points. Therefore, x of k is equal to sigma n equal to 0 to n by 2 minus 1 x of n wn raised to kn plus sigma n from n by 2 to n minus 1 x of n wn raised to nk. Okay, and from the second summation we are taking out wn raised to n by 2 into k. Okay, now what happens? This wn raised to kn by 2, it is equal to e raised to minus j 2 pi by n into kn by 2, which is equal to e raised to minus j pi k, which is equal to cos pi k minus j sin pi k, which is equal to minus 1 raised to k. Therefore, the summation is sigma n from 0 to n by 2 x of n plus minus 1 raised to k x of n plus n by 2 into wn raised to kn. So from the previous slide we got expression for x of k as given in the first line. Okay, and we have another result, that is wn square is equal to wn by 2. It is given on the right hand side. As an example, we have considered w8 square and w4 raised to 1, both are equal. Okay, so using this equation, endpoint DFT can be converted into n by 2 point DFT. That is 8 point DFT can be converted to 4 point DFT, 4 point DFT to 2 point DFT, etc. Okay, so for k even values of k, that is x of 0, x of 2, x of 4 and x of 6, what happens to minus 1 raised to k? That is positive. Okay, so from equation 1 we get x of k as sigma x of n plus n by 2 into wn by 2 raised to n into r. That means endpoint DFT is converted to n by 2 point DFT as shown in equation 1. Similarly, for odd values of k, that is capital X of 1, x of 3, x of 5 and x of 7, minus 1 raised to k is negative. Okay, so as seen in equation 2, x of k is sigma x of n minus x of n plus n by 2 into wn raised to n into wn by 2 raised to n into r. Okay, so as seen from equation 2, this n point DFT is converted to n by 2 point DFT. Okay, and for odd values of k we see that from equation 2 you have one more term, that is wn raised to n. Okay, in when we find out x of k. So as seen from equations 1 and 2, the final x of k DFT is n by 2 point DFT is of x of n plus n by 2 and x of n minus x of n plus n by 2 into wn raised to n. So from the previous slide we saw that for k even and for k odd, the DFT is n by 2 point DFT of x of n plus n by 2 and x of n minus x of n plus n by 2 into wn raised to n respectively. So accordingly we get this structure as shown. Okay. So we see that this is the basic butterfly for decimation in frequency. That is, if the two inputs are a and b, smaller letter a and smaller letter b, then the output capital A is equal to a plus b, and the output capital B is equal to difference of this, that is a minus b multiplied by the twiddle factor, that is a minus b into wn raised to capital wn raised to r. Now we continue with the decomposing procedure. Okay, that is we further decimate n by 2 point DFT into n by 4 point DFT, so we get the structure as shown.
Continuing the decimation procedure and replacing the n by 4 point DFT by butterfly, we get the final structure for 8 point DFT as shown in the figure. Figure shows the comparison of structures of decimation in time and decimation in frequency FFT algorithms. As seen from the figures, for decimation in time, input is bit reversed while output is in natural order, whereas in decimation in frequency, input is in natural order but the output is in bit reversed order. Next difference is that in decimation in time, multiplication takes place before add subtract operation, whereas in decimation in frequency, complex multiplication takes place after subtraction. FFT algorithms find application in variety of areas including correlation, spectrum analysis, etc. By using radix 2 FFT algorithm, we have log n to the base 2 stages of decimation, and each stage involves n by 2 butterflies. Thus, computation of endpoint DFT via decimation in frequency or decimation in time requires n by 2 into log n to the base 2 complex multiplications and n log n to the base 2 complex additions. Both decimation in frequency and decimation in time can be done in place, which means that using a butterfly operation, a pair of complex inputs a comma b produces outputs capital A comma b, and there is no need to store the inputs, and hence we can store the outputs in the same locations as the inputs. Consequently, we require only a fixed amount of storage, that means 2n storage registers in order to store the results of n complex numbers. Since the same 2n storage locations are used throughout the computations of endpoint DFT, we can say that the computations can be done in place. And both decimation in time and decimation in frequency need bit reversal at some place during computation. Now let's consider a problem to find DFT of a sequence, that is x of n is equal to 1 0 0 1 using decimation frequency algorithm. Okay, so here since the length of input sequence is 4, we are assuming capital N to be 4. Okay, and we have drawn the butterfly for 4 point DFT computation. Okay, so x of 0, x of 1, x of 2 and x of 3, the values are to be given the input. Okay, and the final output, as we have seen, we have bit reversal, so the output order will be capital X of 0, capital X of 2, capital X of 1 and capital X of 3. Okay, and once we finish drawing the butterfly, we have to find out the twiddle factors and the required exponentials. Okay, so here the twiddle factors included are W4 raised to 0 and W4 raised to 1. W4 0 raised to 0 is always 1, W4 raised to 1 is minus j. Okay, now the output of first stage, okay, so that it involves 1 plus 0, so that is 1. Again, next value is 0 plus 1, which is again 1, and then next value is 1 minus 0 into 1, which is 1 again, and the last value of the stage 1 output, that is the value at D, is 0 minus 1 into minus j. So minus 1 into minus j, it is plus j. Okay, now output of stage 2, you have simply additions and subtractions at the output. Okay, so capital X of 0 is 1 plus 1, which is equal to 2, and capital X of 2 is 1 minus 1, which is equal to 0. Then capital X of 1 is 1 plus j, and capital X of 3 is 1 minus j. So the output of stage 2 is 2, 0, 1 plus j and 1 minus j, but the output appears in bit reversed order, so we have to make it in the right order. So after reordering, we see that capital X of 0 is 2, capital X of 1 is 1 plus j, capital X of 2 is 0, and capital X of 3 is 1 minus j. Okay, and the final output should be written using curly brackets. That's all. So the answer is 2, 1 plus j, 0, 1 minus j. So next we are going to see another problem to find the DFT of given sequence with n number of values in the input sequence, that is 1 2 3 4 4 3 2 1, using decimation frequency. So first we have to draw the butterflies. Okay, then we have to find the values of the required twiddle factors, W8 raised to 0, W8 raised to 1, W8 raised to 2 and W8 raised to 3. Okay, so the input is in the exact order, output is in bit reversed manner in using decimation frequency. So we can apply the inputs 1 2 3 4 4 3 2 1 as shown. Okay, and then the outputs of the stage 1, then the outputs of stage 2, and the final output after stage 3 can be computed, and it will be always better to use the tabular column as shown in the next slide. So accordingly, the output of stage 1 is 5555 minus 3 minus 0.707 plus j 0.707, then minus j, and minus 2.12 minus j 2.12. The required twiddle factors are computed and it is written as shown. W8 raised to 0, W8 raised to 1 is 0.707 minus j 0.707, W8 raised to 2 is minus j, and W8 raised to 3 is minus 0.707 minus j 0.707. So output of stage 2 is as shown, that is 10 10 0 0 minus 3 minus j minus 2.827 minus j 1.414 and minus 3 plus j and 2.827 minus j 1.414. Then output of stage 3, that is 20 0 0 0 minus 5.827 minus j 2.414, then minus 0.173 plus j 0.414 minus 0.173 minus j 0.414 and minus 5.827 plus j 2.414. So since the output of stage 2 is bit reversed, we have to reorder, and the final output is as shown. Final reordered output is 20 minus 5.827 minus j 2.414, then 0, and minus 0.173 minus j 0.414, then 0, minus 0.173 plus j 0.414, then 0, and minus 5.827 plus j 2.414. Okay, and the final output has to be written using curly brackets as shown in the next slide. So this is the final answer to the problem discussed. Now next we shall discuss how to find out inverse DFT using FFT algorithms. So FFT algorithms can be used to compute inverse DFT without any change in the algorithm. Now by definition of DFT and IDFT, we have x of k is equal to sigma x of n e raised to minus j 2 pi k n by n, and inverse DFT, that is small letter x of n, is 1 by n sigma x of k e raised to j 2 pi k n by n. Now if we compare these two equations, we see that the difference is in the twiddle factors, or we can say that the twiddle factors are conjugates, and inverse DFT has a multiplier term, that is 1 by n. Therefore, we can conclude that the existing FFT algorithms can be used to find out inverse DFT by interchanging the inputs and the outputs, and replacing the twiddle factor by its conjugate pairs, and finally multiplying the answer by 1 by n. Now you will understand more when we see problems. Next we shall see a problem to find 8-point inverse DFT of a sequence that is given using decimation in frequency algorithm. Okay, so in decimation in frequency we know the input is in the correct order, so we'll first draw the butterfly structure of the first stage. Okay, and the inputs are written, that is 4, 1 minus j 2.414, 0, 1 minus j 0.414, 0, 1 plus j 0.414, 0, 1 plus j 2.414. Okay, and as discussed earlier, the twiddle factors are conjugates. So in actual FFT computation using decimation in frequency algorithm, we have w8 raised to 0, w8 raised to 1, w8 raised to 2 and w8 raised to 3. So instead of that, here what we are doing is we are going to use the twiddle factors w8 raised to 0, w8 raised to minus 1, w8 raised to minus 2 and w8 raised to minus 3. So these twiddle factors are computed and as shown in the right hand side. Okay, then we follow the same procedure of finding the outputs of stage 1. We get the following outputs, that is 4, 2 minus 2j, 0, 2 plus 2j, 4, 2 minus 2j, 0, 2 plus 2j. Now coming to the second stage, here also the twiddle factors w8 raised to 0 and w8 raised to minus 2 twiddle factors are written, and the same procedure as a normal FFT computation that is followed. So the outputs of stage 2 are 4, 4, 4, 4, 4, 4, 4, 4. Now coming to the last stage, so here the outputs obtained are 8, 0, 8, 0, 8, 0, 8, 0. Okay, now from the equation for inverse DFT we have a 1 by n term, so we have to multiply by 1 by 8. Okay, and we get the output of the final stage as 1 0 1 0 1 0 1 0, and since this output is bit reversed, we have to reorder, and on reordering we get the final output as x of n is equal to 1 1 1 1 0 0 0 0. Now these are the main references, and thank you for your patient listening.